All right, for our next card, we're going to talk about the sum or difference of cubes. It is two formulas in one. This is the other binomial type of problem that we do have to factor more because we do have a rule or a pattern with it. If we notice, it's in the form of a cubed plus minus. So that means there's two formulas in one. One, we're following the top rule, so it'd be a cubed plus b cubed. And the other formula would be a cubed minus b cubed. So that plus or minus means that there's two formulas in one problem. This is another problem that we're going to have a checklist that we're looking for specific stuff, and then we're going to follow a pattern, and basically it's a formula. So the problem we're going to look at is 27x to the 6th, y to the 64th, and our checklist is the first thing we're looking for. So the checklist we're looking at is all exponents have to be multiples of 3. All coefficients have to be perfect squares, or perfect cubes. And our perfect cubes are 1, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. And then 64, 125, 216, 343. That's through 7 cubed. Now, it's useful to know through 10 cubed. There could be, those are ones that I see in problems a lot. And then the 8 cubed would be 512, 9 cubed is 729, and 10 cubed is 1,000. You could see bigger ones, but knowing through 6 or 7, recognizing it is usually enough, but then you could always write more if you wanted to on this card. So looking at my problem, I have exponents that are multiples of 3, because 6 is a multiple of 3. The other term doesn't have a variable. The coefficients are perfect cubes because 27 is 3 cubed and 64 is 4 cubed. It's also a perfect square, but looking at this problem, I have a plus sign and I have the 27 isn't a perfect square, so I definitely don't have a difference of squares. So this is one of the things that you do have to be careful with some of those numbers. Both 1 and 64 are both perfect cubes and perfect squares, so be careful. Then we're going to look at our steps. So like all problems that I have for factoring, my first step is always to check for GCF. In this case, I don't have anything that divides both into 27 or 64, other than 1. And then I don't have any repeated variables in both terms, so there is no GCF on this one. A lot of times we get to the point where it's not showing, the GCF won't be part of the problem because we're focusing on one type of factoring, and that's kind of the case here. So we have a sum of cubes, and now we're going to look at the actual pattern for the formula once we've looked at the GCF, which we don't have. So my first step or second step in looking at my actual steps is I'm going to write one set of parentheses. This is going to be a smaller set of parentheses, and I'm doing the cube root of the first term is going to be in the front of the parentheses. I'm going to use the same sign as what I had in the problem, and then the cube root of the second term is going to be at the end of the parentheses, and I'm going to divide all exponents by 3. So 27 is 3 cubed, so I'm going to put the 3 down, and then x to the 6th, I'm dividing the exponent by 3, so I get x squared, and 64 is 4 cubed, so I'm putting the 4 down there. So it's going to be make the next set of parentheses, which is we're using the parentheses we just wrote, and the formula or the pattern is we're going to square the front, we're going to do the opposite of the front times the back, and then we're going to square the back. So that's going to give me 3x squared times 3x squared. The opposite, so minus 3x squared times 4, and then plus 4 times 4. And that will give us our final answer, which is that first parenthesis, so the 3x squared plus 4 times the quantity 9x to the 4th minus 12x squared plus 16. So looking at the pattern, I'm only going to have one negative sign. It'll either be in that first set of parentheses or it'll be that first sign in the second parentheses. And the trinomial that I'm left with in that second set of parentheses will not be factorable. So writing the last bit, we're going to write the formula generically. Remember, it's two formulas in one. So on the back of the card, I decided to write the formulas. Sometimes you could put an extra example on the back side of your cards, but for this case, I want the formulas to be together so that I can see it. So the generic formula that you're going to see in most books is we're going to have a cubed plus or minus b cubed, meaning they're putting those two formulas together, equals a plus or minus b, meaning we're following the top if we're adding, we're following the bottom if we're subtracting, and then it's a, the second parenthesis would be a squared minus plus. So it's changing signs for that next one, and then a times b plus b squared. I did write the formula separately, one with the plus and one with the minus, just so that you can see what those formulas are. I do recommend getting used to that plus minus and the minus plus. However, if you are not going into trigonometry and the calculus stuff, you probably won't see that too often. So it is perfectly valid to write the two formulas together. Just be aware that they are equivalent. This is two formulas. We're just lazy and wrote it as one. And it is these two formulas that are in that one formula.